system is completely isolated and you do a microcanonical simulation. In many cases, of course, you want to simulate a system at final temperature and you want to heat up your system and you want to find ways of keeping the temperature constant. So the simplest way, which is used in many instances, is just to rescale the velocities. So what do I mean by rescaling velocities? You correct the velocity that you are computing in your system at each step to give a certain desired temperature. So you actually use a scaling factor that I call your lambda, which is the square root of the temperature that you're trying to reach, TW, T wanted, divided by the temperature at time t. No, of course, okay, so, because t is a thermodynamic quantity, so a temperature at time t in principle has zero meaning, right? So by temperature at time t, we just mean what sometimes one calls kinetic temperature. So just the value of the variable t derived from the velocities of the particle at a certain time t. So it's not the temperature in a thermodynamic sense. Okay, so you rescale the velocities by this factor here, and the algorithm is extremely simple, but it's quite crude and may inhibit equilibration. Again, if you rescale your velocity, for example, if you rescale your velocities and depending on how you rescale your velocities and how you tune this parameter, and really depending on the vibrational spectrum of your system, you may end up in a situation where reaching equipartition is quite difficult. But still, this very crude algorithm is used in many instances to start heating up your system, to start having your atom moves and bringing them to a final temperature, and then you may want to switch to another algorithm. So one of the first schemes, and again, one that is still used, that was proposed by Berenson, and here is the paper, to put your system at a certain, take your system at a certain temperature, is the following. You actually assume that, like in real life, when you want to put a system at a certain temperature, you put it in contact with a heat bath, right? And what you do, you actually exponentially scale the velocities at each time step by a certain factor, which is determined by the temperature that you want your system to have, which is the temperature of your heat bath. And also here you have a parameters which tells you how fast you want to reach the temperature of your bath. So it is actually not dissimilar from a simple velocity rescaling. Is quite simple. And again, you do not, as in the case of the velocity scaling, do not sample the canonical ensemble. Okay? So you are doing a molecular, so if you are simulating a isolated system, not in contact with any heat bath, not rescaling anything, you are sampling, if you just go for times long enough, a statistical ensemble, which is a microcanonical ensemble. If you're doing this, you actually heat up your system, you put your system at a certain temperature, but you're not sampling any statistical ensemble. So you have to keep this in mind and when you interpret your result.
Why is this happening? Why is this happening? Does it have a constant temperature? Or
I'm sorry?
Why is this not something you can ensemble?
Because if you actually look at the partition function of the system, you see that the partition function of the system like this is not the partition function of the canonical ensemble. So in order, it's not sufficient to sample the canonical ensemble to actually reach a constant temperature. That's but there is a way to sample the canonical ensemble, and here it is. So this was introduced by Nozé in 1984. It's called the Nozé thermostat. And here we introduce a concept which is very, very important, and which is a concept that you will find again tomorrow when the Karp-Parrinello method is introduced. I in terms of concept, not in terms of what you want to do. And the concept is that you want to introduce a new variable, a physical variable in your system, and introduce it by introducing an extra degrees of freedom. So conceptually, this nozzle thermostat is totally different from rescaling of velocities or from the variance and skiing or from everything that was done before. Before, the concept was, let's actually modify the variables, classical variables that are the velocities, determining my temperature so as to bring the system to a certain temperature. The idea of nozzle, again, it is philosophically really totally different, is let me actually introduce an extra degrees of freedom, which then acts in such a way that I do modify the velocity of my system, but an extra degrees of freedom which describe the fact that my system is in contact with a heat bath. And then I actually write down equation of motion for the system, which is composed by my atoms or ions or molecules specified by the position Ri, plus an extra degrees of freedom. So I do have a kinetic energy and a potential energy associated to the extra degrees of freedom. This, from the philosophical point of view, is totally different from anything that was done before. It's the same concept that we'll find in 5 minutes when we talk about constant pressure in the Anderson formulation. And it's vaguely the same concept that you will find when tomorrow you will see the Carr-Parinello method to do a Venetian molecular dynamics. There are extra degrees of freedom introduced in the system to describe something happening to the system. Okay? So here, our system is not only the system described by the coordinates of the ion, but it's the system which is coordinate of the ions plus the S variable. And so we write down a total kinetic energy of the system and potential energy, which includes here a kinetic energy of my extra degrees of freedom. And multiply this is 1/2, the mass-like associated with the extra degrees of freedom times the velocity of my extra degrees of freedom. So this is not a mass. The unit of that number are not a mass. And it's a mass-like parameter which measures the coupling between the reservoir that physically you want your system to be in contact with to acquire a certain temperature and your system. And this is a parameter that you are introducing that you have to control, which is not easy to control at all, and which should never be considered hardwired in your simulation when you use another thermostat. It doesn't have, it should not be too high, otherwise there is a slow flow. I mean, the system cannot equilibrate very well, and it should not be too low. So in his paper, Noze actually proved that if you have a system composed by your ionic coordinates, represented by the ionic coordinate of your system and the extra degrees of freedom, with the extra degrees of freedom having this kinetic energy associated and this potential energy, you see this is kind of an entropic term. You see that? This is the number of degrees of freedom in the system. This is the wanted temperature, and this is the logarithm of your degrees of freedom. This is really an entropic term that you're adding to your Hamiltonian with this degrees of freedom. If you consider the coupled system with this S degrees of freedom, then you can show that the partition function of the coupled system, okay, all the Ri plus S, is actually related to the partition function of the canonical ensemble by this expression here. And then you can prove that the method, if you do the simulation using the Nozer thermostat, allows one to sample the canonical ensemble. Now, this looks very nice, and it is, in principle, very nice, because you have a method that allows you to keep the temperature of your system constant, and also to sample a physically meaningful, statistically meaningful ensemble. But again, let me remind you that the choice of this parameter is highly non-trivial. And if you do not choose that parameter well, you can actually physically couple these degrees of freedom with some of the vibrational mode of your system, and actually you may end up not doing meaningful simulations. So very often it's said, oh, I'm using the Nosret thermostat because it's so wonderful. I have this sampling of the canonical ensemble, and I feel so good about that. You should feel good about being able, of course, to sample the canonical ensemble, but in order to do a meaningful simulation, and by meaningful, I mean a simulation where you really have equipartition of energy and the dynamics of your system is not too much perturbed. It's not easy, and the choice of this parameter is actually highly non-trivial. And it also depends on the temperature when you vary the temperature in your system.
So, in this extra degree of freedom, in the limit Q goes to 0, does it exactly corresponds to the canonical?
No, if you do not, if Q goes to 0, basically you do not have any coupling anymore. And so you go towards the microcanonical ensemble.
So in a sense, from isolated, you are going to a sort of open system by introducing Q, isolated to a closed system by introducing U. That means you are tending from microcanonical towards the canonical.
Yeah. Yeah, if you, but it's not that you tend. Okay, so you are sampling. So what I was trying to say is that by using this formulation, you can show that the partition function of the coupled system is actually related to the partition function of the canonical ensemble in this way, and you do sample a canonical ensemble distribution. This doesn't tell you that actually you are doing a simulation of your system, which, for example, from the point of view of the dynamics of your system is meaningful. Or faithful to representing really the physical property of your system. That's what I'm trying to say. So if you choose properly this parameter so that you couple your system to the reservoir not too much to perturb the dynamic of your system, but not too little in such a way that you're still able to have a flow of energy in such a way that you do heat up your system, then you're fine. And I'm completely aware that I'm giving you a total hand wave argument here on how you should choose Q, but I don't know of any real rules on how to choose Q. It depends on the system, and it's a very difficult. Let me give you this example here that is actually taken, and then we'll get back. This is an example which is taken by old simulation that at the very beginning when he came up with this idea, actually Nozé himself presented in some of his papers. And these are, this is the same system. Let me see if I remember the system. This is the same system, which is 108 argon atoms with a Leonard-Jones potential. And this is what happens to the oscillation of the temperature of the system by two different choices of Q. This is a small Q, and this is actually a large Q, which turns out to be more or less a reasonable choice of Q for that system. And you see this system is not an equilibrated system. It's still a system with damped oscillation and so on and so forth. And this system is a system which starts to be well equilibrated. And here, these systems in these two examples had been simulated for the same length of time. so the choice of Q actually can determine very much what happens to your system. And by the way, every time you compute it, you want to compute dynamical properties, even the simplest one. And we'll touch upon those later on. Even the self-diffusion coefficient. If you have a thermostat on your system, even an oscillator thermostat, you should be very careful because your dynamical properties may not be met.
Which is better in these two?
So in this case, if you actually continue the in this case, the better Q is the higher Q, where you start having the system, the oscillation of the system, regular oscillations, and an average temperature like so. So if you continue actually this simulation here, this system, it turns out, never equilibrates. There are these wild oscillations of the temperature in this system. So to really look at what is better, you should not only look at the temperature here and here, but you should really look at how equipartition of the temperature, equipartition of energy occurs into your system. And so especially if you have a two-component system, look at whether the energy is distributed equally in each degrees of freedom of your system. And sometimes, actually, many people actually just look, there are papers that you find, okay, well, let's look at the temperature. The temperature looks cool, and it looks like, there are regular oscillation, and even for more than one component system, and it looks fine. But really, to see whether your system is fine, you have to ask a question: do I have equipartition of energy? And you have to look at each degrees of freedom and check that.
But it is also generally believed that a kind of white noise in nature is more occurrence than other noise. So this pattern also look like white noise, flat. So
yeah, but I could actually I could show you simulation that we have done ourselves of systems who are not equilibrated at all, actually. And I have one example, painful example in mind of liquid water on a graphite surface where the temperature would look beautiful, and there's like a beautiful profile of temperature, and then you go and analyze how the equipartition of energy has occurred, and the equipartition is not there, and the system is not equilibrated. We have examples of that.
I guess I'm not really clear on, seems like you're making a distinction between properly sampling the ensemble and getting meaningful dynamics.
Yes.
Is it just that you might choose a Q that gives you very small temperature oscillations, but then you're damping out any realistic fluctuations?
Yeah, you are. Yes, I'm making. So I was making exactly this difference in the sense that these are two different things. I mean, you can have a good sampling of your canonical ensemble. You may also have a good. You may have fluctuations such that your thermodynamic properties actually are computed correctly. For example, if you want the temperature, the pressure, the enthalpy of your system, and whatnot. But then if you go and look at the dynamical property of your system, even the simplest one, like self-diffusion coefficient on the liquid, this may not actually be meaningful. Or, much more difficult, if you look at the vibration of your system, say that you want to do a phonon, not a phonon in a liquid, but a vibrational spectrum or higher spectrum or whatnot, even if your thermodynamical properties are all right, this may not be correct. And this is very important because it is also in the nature of molecular dynamic simulation. That is, you may have a simulation which is carried out well enough to compute certain properties, for example, thermodynamic properties, and it's not because your thermodynamic properties are computed correctly in terms of the error bars that you have, in terms of the convergence that you have, that your dynamical property will as well be computed correctly. So it's not enough. Each property has to be checked And in order to understand whether you computed correctly or not, you have to check what you do to your system to keep the temperature, for example, or the pressure will get there at a certain value.
It may also so happen due to the wrong choice of the potential, all this can be carried out.
Oh, I'm talking about at fixed potential. The potential is, you choose the potential, and this is one choice that you have made, and then this is another matter, really. There was another question.
Yeah, I just wanted to clarify to make sure I was understanding correctly. When Q approaches 0, you actually have like almost an instantaneous coupling, right? And when Q gets large, then it's almost as if you don't have coupling. Is that correct?
So, if Q, yes, it is correct. So if Q,
so if Q was 0, I think you said earlier that if Q was 0, you would not have coupling.
let me. So if I have, a very, very high Q, I have a very, very slow coupling.
Yeah. So
I have a very, very, very slow coupling. And then if I have a very small Q, I kind of kick the system right away. And so if I said something different, I think that what I said right now is correct. So the very, very high Q, basically, the heat flow is very, very, very slow. Sorry for the confusion. I may have said something not quite correct before. Okay, so I think I wanted to finish that before going to the pressure, but I think that we'll stop here because it's 10:30, and then when we reconvene, I'll tell you about coupling the system with the barostat to keep the pressure, and then we'll take it from there. Okay, that's. And I understand there are no cookies in the morning, right? Okay. So, well, enjoy coffee, I guess.